completely new topic, chapter 5, right? We did the applications of exponentials, and it kind of tied into chapter 4 a little bit. But chapter 6 goes in a kind of opposite direction because we're undoing derivatives now. We just have 4 different ones that we can do, so let's talk through those different rules. So, the first one we want to talk about is the power rule, right? It's the first derivative we started with, so first antiderivative that we'll start with. That's what they call it, antiderivatives or integrals. I kind of use both interchangeably, and so they mean the same thing. So let's remember the derivative rule. For the power rule, we have a coefficient x to the exponent of n. So we would multiply the power down and then subtract 1 from the power, right? So then the notation is this kind of squiggly s thing, right? The integral of ax to the n dx is just like kind of the finisher, just like the d over dx, okay? Just means x is your variable, okay? So what we do is we do the exact opposite. The last thing we did was we subtracted by 1. So that means we add 1. So we do ax to the n plus 1. The previous thing we did was multiply the power down. So now we divide by the new power. So we divide by the n plus 1. Now there's one other little thing we have to talk about. When we take the derivative of something, right, constants go away. So if we take the antiderivative, we don't know if a constant was there or not. So we just kind of have to account for it in kind of insurance almost on if there was something there or not. We don't know. So we just say plus c for constant. Okay? These just give us a formula, right? So anytime we get a formula for an antiderivative or an integral, we just do plus c. 6.2, the next section, if we actually were calculating something, we wouldn't do plus c because, well, plus c isn't a number. We're not calculating anything if we don't know all of it, okay? So, the next one is kind of a variation of this. It's the more basic version if we just had a coefficient with just an x. The derivative of ax is just a, okay? We specifically mention this because we have the integral of just a constant. Well, it has to kind of get its x back, okay? It gets the variable back. So, ax plus c. We can always check our answer by taking its derivative. If we take the derivative of this, we should get back to a. If we don't get back what we started, well then we did something wrong, right? Either in our derivative or our antiderivative. Usually, by now, right, we should be pretty good with derivatives. So that would mean check your antiderivative. Next rule is, well, there's one other thing that might happen with x's, right? What if they're in the denominator? Generally, we can move them back up, and then it's okay, and we just use the power rule, just like before. But, however, I'm going to start with the antiderivative on this one for a second. If we have a over x, well, really, we want to think about this as ax to the negative 1, right? Well, then, if we did the power rule with it, plus 1, well, that'd be x to the 0. That'd be getting rid of an x, right? Doesn't really make sense because derivatives make x's go down in power, right? They kind of get rid of x's in a way. All of this is kind of giving x's back. You're getting more x's. So we will never get rid of an x when we take the derivative, okay? So we do not do this method. When we took the derivative to get something like this, the only thing that did that for us was an ln. So, if we took the derivative of a basic ln, just a coefficient ln of x, what we would get would be a, because we rewrite the coefficient times the derivative of the inside. Inside's x, so derivative is 1 over that inside. Simplify it out to be just a over x. Well, that's exactly what we're starting with. So that means we need to go backwards. So that means we get a ln of x plus c. Except for one little thing. So, on this, we can plug in whatever we want for x, right? Negative or positive. So it doesn't matter. But we cannot take the natural log of a negative number. So we have to fix it by just putting absolute values on it. Okay? Now, very last one. We just learned it recently. We don't have it on here yet. Exponential. So, the derivative of a basic exponential with just kind of the same setup as chapter 5, almost. Derivative here, well, derivative for e is we look at the exponent, we take its derivative, and multiply it down. So the derivative of kt is k. Multiply it down, right? So we have a times k, keep it, e to the kt. So all we did was multiply. So when we take the antiderivative of a e to the kt, I used t. That's okay, we can use t. Doesn't matter what variable we use. So, taking the antiderivative of this is, well, we look at the exponent, take its derivative, same thing as before for a derivative, right? Except now, instead of multiplying, we divide. So it's a e to the kt, all divided by k, plus c, of course, still. These are our rules, okay? So, for a couple examples, we want to take the integral of 9x to the 8th dx. Well, we see that this is a power rule, right? Whatever rule generally that we would have used for the derivative, we use for the antiderivative. So, we take the integral and we say, okay, rewrite the coefficient, x to the plus 1 to the power, so 8 plus 1 is 9, and then divide by the new, plus c. Except then we can simplify, right? The 9's cancel. So really, this is just x to the 9th plus c. Okay? Well, let's check it. Let's take its derivative. Derivative of x to the 9th is 9x to the 8th. Derivative of a constant goes away. So we just have 9x to the 8th. It's exactly correct. Okay? The notation of maybe what we call this is if this started out at f, right? Just regular f of x, this would be capital F of x. Okay? So essentially what happens is if we start with f, then we could take its derivative and get f prime, or we could take its antiderivative and get capital F. Okay? So, or we could be given the derivative, take the antiderivative to get back to the original. Okay? So this direction would be antiderivatives, this direction would be derivatives. Alright? So, then, next problem. If we have the integral of e to the 3x minus 4x plus 3 dx. So, multiple terms, just hit them one as they come. Okay, same as derivative. So, e first, look at its exponent. 3x derivative is 3. So that means we rewrite what we have and then divide by 3. Then, starts off with a 1 exponent. So we add 1 to it. So that means we have 4x to the 2 divided by 2. Then, constant. Constants get their x back. Then plus c. Then we look to see if we can simplify. 4 over 2, that simplifies to just 2, right? So then, our antiderivative is e to the 3x over 3 minus 2x squared plus 3x plus c. Okay? That is a general formula still though, because of the plus c not being an actual value, which we can find. It's very simple to do. So let's do that next. So if we're given the derivative of f of t is t squared minus 5t minus 7, we want to find f of t if f of 0 is equal to 2. So, we're given f prime, we want to find f. We're coming back to the point. So that means we need to find the integral of the function, the derivative function. So the t squared minus 5t minus 7 dt. Now, taking the antiderivative, start off with the t, it's squared, so then it becomes cubed over 3. Minus 5, started off at 1, so it's t squared over 2. Constant, so minus 7t. Don't forget the plus c. So this is f of t, capital F of t. Lowercase f of t. Now, they tell us that f of 0 equals 2. That means if we plug in 0 for all the t's, we should get it equal to 2. So 2 is equal to, well, 0 makes this 0, also 0, also 0, so c. Oh, look, we found what c equals. Because they gave us a point, that means we can know what c is. Sometimes it might not be 0, so we might have to simplify all of this and actually solve for c, but that's what c is. So the actual function of f of t would be t cubed over 3 minus 5t squared over 2 minus 7t plus 2, because that's what c is. That's the full function. Okay? So this is pretty much 6.1. There's some other parts to it, but that's the generality.